Okay, let's talk about relations in math. A relation in math is similar to a relationship. It's just the way in which two or more things, concepts, objects, or people are connected. And in math, what we call a relation is a set of ordered pairs, so one variable associated with another variable, that indicates the association between elements of an input variable with the corresponding elements of an output variable. We'll get into the meat of that sentence in a little bit, but the basic thing to remember is always in a relation, there is a relationship or an association with an input and with an output. A relation can be represented in a number of ways, and we'll go through all these ways: words, table of values, ordered pairs, diagrams, or graphs. Let's look at the following scenario. You have a fruit vendor, so someone's selling fruit at a stand, and they have the following fruit: red apples, green apples, oranges, blueberries, raspberries, bananas, and tangerines. And we want to show that relation in words. Well, the relation that shows the association of a set of fruit to a set of colors would look something like this. Apples at the stand are red. Apples at the stand are green. Oranges at the stand are orange. Raspberries at the stand are red. Bananas at the stand are yellow. Tangerines at the stand are orange. But generally we don't like using words too much because you can see that's kind of cumbersome. So we come up with other ways to show the data, like a table of values. And in a table of values, what we'll do is we'll have the input variable, which is your fruit, on the left, and the color of that fruit on the right. So the input variable is the independent variable, you call it, and the output variable is the dependent variable. So the color depends on what fruit you're talking about. And then we just list those variables under the respective columns. So for fruit, we have apples that are red, you have apples that are green, oranges that are orange, raspberries that are red, bananas that are yellow, and tangerines orange. So a table of values is a nice clean way of displaying your data that says, okay, on the left side is my independent variable, my input, and on the right side is the corresponding output. With ordered pairs, you would just list those associations within a set of brackets with, again, the input variable or the independent variable is always on the left side. You separate it with a comma and then the output variable on the right side. For mapping diagrams, also called arrow diagrams, you'll see why shortly, what we'll do is we'll draw two sets of ovals, one on the left and one on the right side. On the left side will be your input set of elements. On the right side, you'll have your output set of elements. And when you fill out the left and the right ovals, what you'll do is you'll list the elements of the input set in alphabetical order, that's on the left, and list the output set in alphabetical order, that would be on the right. And then you draw arrows to show the association between each variable. Now, if you were dealing just with numbers instead of words, we would order the numbers from least to greatest. So let's see how that would look. In our case, we'll put all the fruit on the left side. So we have apples, bananas, oranges, raspberries, tangerines. On the right side, we have our colors. And you'll see how we reordered it all to be in alphabetical order. Now all we do is draw arrows from the input set to the output set. So for apples, well, apples, there's green apples and there's red apples at the fruit stand. Bananas, well, there's only yellow bananas. Oranges, oranges are orange. Raspberries, red. Tangerines, orange. Notice also that the arrows only go in one direction. They go from that input side and point to the corresponding variable on the output side. They don't switch back. So we're not pointing the arrow from red to apples, for instance. We point it from apples to red. It's always input that will determine the output. Now here's an example you can try. You have a digital clock it displays digits between 0 and 9, inclusive, by lighting up different segments. For example, the digit 2 would need 1, 2, 3, 4, 5 segments to light up. So how would you list a set of ordered pairs of the form digit is your input, and depending on the digit, the number of segments that lights up, that's your output. So think about all the ways that you can make the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 by lighting up different segments of the clock and list them as a set of ordered pairs. Then try to represent that relation as a table of values, and then try to represent that relation as an arrow diagram. See how you do and compare your answers to mine. So for ordered pairs, you have an input of 0. 0 is going to take how many light segments? 1, 2, 3, 4, 5, 6. So 0 would need 6 light segments. The number 1 would need just 1, 2 line segments. The number 2, we said, needs 5 line segments. The number 3 would need 1, 2, 3, 4, 5 line segments as well. And it goes on and on until we reach number 9. So I'm going to go through the other ones fairly quickly. 4 needs 4 segments. 5 is going to need 5 segments. 6 needs 6 segments. 7 needs only 3 segments. 8 needs 7 segments. And finally, 9 needs 6 segments. And that's your list of ordered pairs. Always the independent variables, the 0 to 9, these are the inputs or the independent variables. Those go on the left side of the brackets. Then you put a comma down, and on the right side is your outputs, which in this case it is the number of segments that you need to light up. Okay, now for a table of values, what we would do is we would say, okay, here's the digits, that's our input. We'll make that on a table on the left, and on the right side we'll have the number of segments that's needed to light up. So 0 needs 6 segments, 1 needs 2, 2 needs 5 segments, 3 needs 5, 4 needs 4. I'm going to have to do a second table here. Digits, segments again. Apologize for the lack of room, and we're going to just continue on. So 5 needs 5 segments, 6 needs 6 segments, 7 needs 3 segments, 8 needs 7, and 9 needs 6. And again, the important thing to remember here is inputs on the left and outputs on the right. And for your inputs, the inputs need to be from least to greatest. Same thing with an arrow diagram. So let's do our arrow diagram. Numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's our input set. On the right would be our output set. And we would order this from least to greatest too. So here we have, let's see, we start at 2, there's a 3, 4, 5, 6, and 7. Those are all the possible outputs. And we just draw the arrows to associate the inputs to the outputs. 0 needed 2 segments, 1 also needed 2 segments, 2 needed 5, 3 needed 5, 4 needed 4, 5 needed 5, 6 needed 6, 7 needed 3, 8 needed 7, and 9 needed 6. And so those are 3 ways right there to show that relation: ordered pairs, table of values, and arrow diagrams. Now, a major way we're going to show relations is by graphing. So let's take a look at that. In this situation, we have Kalkadan. She rides her bike to school every day. The table of values is going to show her distance from home. So when she first leaves her house, she hasn't yet left her house, she's about to leave. When the time is 0 minutes on the stopwatch, she has traveled nowhere yet. After 1 minute, she has traveled 250 meters. After 2 minutes, she's 500 meters away from home. After 3 minutes, 750, etc. Now, to represent this relation with ordered pairs, simple enough. 0 minutes, 0 distance. 1 minute, a distance of 250 meters. 2 minutes, she'd have traveled 500 meters. After 3 minutes, she'd have traveled 750 meters. 4 minutes, 1 kilometer. 5 minutes, 1,250 meters. That's simple enough. Now let's graph this relation. So when graphing, know that each of those ordered pairs represents a point on the graph. So the 0, 0 is a point, the 1, 250 is a point, the 2, 500 is a point, on and on and on. And each of those points, right, they belong somewhere on this graph. Now, how do we find out where they lie? Well, that first number, so the 0, the 1, the 2, the 3, the 4, the 5, those are all elements of the input set, or your x value, which just means how far along the x-axis or the horizontal axis does that point lie. Whereas the second number, the number on the right, is the related element in the output set. It's your y value, how far up or down that point lies along the y-axis. So let's look at 0, 0. 0, 0 means that point's going to go across until it hits 0 on the x-axis, and 0, and then it's going to go down the y-axis till it hits 0 on the y-axis. So this is where the point 0, 0 belongs. The point 1, 250, that first number 1, means it goes all the way to the 1 line on the x-axis, and then it goes to 1 on the x-axis, and then it goes to 250 on the y-axis. 250 is right between the 0 and 500. So 1, 250 should lie right here. 1 on the x, 250 on the y. 2, 500, that point is going to go all the way to the 2 line, and then down on the x-axis, and then down to the 500 line on the y-axis. 3, 750 goes to 3, and then 750. 4, 1000, 4 along the x-axis, and then 1000 along the y-axis. Finally, 5 and 1250, that's 5 along the x-axis, right? 5 along the x-axis, all the way to 1250 on the y-axis. So those are your 5 points. Now what we can do here is we can actually draw a line that goes between all those points, or through all those points, because we know that when you ride a bike, you don't all of a sudden jump from 250 meters to 500 meters to 750 meters. You must go from 250 meters to, 251 meters, and then 252 meters, and 253 meters. We say this data is really continuous, so we're able to draw a line through all those points. And that's your introduction to graphing. We'll do more of this in later lessons.